So let's start our second evening talk, and it's my pleasure to present Yuval Perez from Microsoft Research. It's a great pleasure. And I think Yuval is one of rare persons who beats me in number of travels.
I can't quite believe that, but there's a story of two planes crossing over the Atlantic, and Vladas was in both of them. So. At least people in both planes claim that. So. Okay, good evening. It's a real pleasure to be here. What I'll be describing is joint work with Alistair Sinclair from Berkeley, Alexander Stauffer, also from Berkeley, who just finished an internship, or is close to finishing an internship at Microsoft Research, and Perla Susi in Cambridge, who is also visiting Microsoft. So his title is Mobile Geometric Graphs. So this is a dynamical version of the well-known random geometric graphs, also known as the Boolean model and continuum percolation. So the basic picture we start with at time 0 is a Poisson process in the whole plane with fixed intensity lambda, and we can make it into a graph by connecting two vertices if their distance is less than r. So that's the usual random geometric graph or Boolean model, and you can realize that by drawing little disks of radius r/2, or balls if we're in higher dimension. So many of the things apply in higher dimension. I will focus on the two-dimensional case, which turns out to be the most interesting. So, so we just draw these little disks, and then two disks intersecting correspond to an edge between the two nodes. Okay, so that's the random geometric graph, and we'll be considering a dynamical version of that where the nodes move as Brownian motions, as independent Brownian motions. And one basic fact which we'll use throughout is that the measure we started with is stationary for this dynamics. Okay, so that's classical and well known. There are many ways to prove it. In some way, a very elementary way is if you first think in finite volume in a torus, what's Poisson process in a torus? You just take a Poisson number of points according to the area of the torus times lambda, and then just this Poisson number you just spread uniformly. So you can think of once you fix the number, it's just independent points. Now, if you take on the torus, because of translation invariance of Lebesgue measure, it's clear that if you have 1 point and it's moving by Brownian motion, if it started according to Lebesgue measure, then at any time its distribution will be Lebesgue measure, because you're just adding some Gaussian modulo the side of the torus to a point. So since each point, when you translate it, it will still have the uniform distribution, the whole process is invariant, because the number of points isn't changing. And once you know this in the torus, you can just pass to a limit and get the result in the whole plane. There are many other ways to see this if you know more about Poisson random measures. Anyway, this is also very intuitive. You start with Poisson. Brownian motions keep it stationary. So at any time, if this is the picture we started at time 0, at time s, we'll get a different picture, but with the same distribution. So in this model, there are many questions, many interesting questions, and it hasn't been studied as much as, of course, the one at fixed time. We'll, in this talk and in the corresponding paper, we focus on 3 problems: detection, coverage, and percolation. So the detection one is how long till a target gets detected by the system, namely if you have one more disk, which you can think of as fixed or moving, how long till it meets one of the disks of the graph? So we're distinguishing one special disk here, the gray one, that we're focusing on, and we want to know how long till it meets one of those, one of the points of the Poisson process, when they're all moving. So, well, if you just act, typically this is some constant, that we don't care about the value of the constant. So what we care about is what is the chance it will take a really long time. So this is actually the motivation for some of this topic comes from the study of mobile wireless networks. But this is a case of this saying that the purpose of reality is to inspire good theories. So we're not making any claim that the theories here actually are related to the original reality that inspired them. So, okay, so at some random time t detection, let's see this, right? The gray disk is detected by the other, or touches the other disks, and we want to know the tail of this variable. So of course, at a fixed time, say the probability that at a fixed time the particle is detected is just the probability, or the particle is not detected is just the probability that it's outside a disk of radius r. So that's e to the minus lambda, the area of the disk. But we're interested in the dynamical version. What's the probability that the detection time is bigger than some t? Now, for a non-mobile target, so if the target is fixed, there's a classical formula that gives the answer. And as classical as it is, it should be better known. So let me explain this formula. So you can find this in a more general form in the book on stochastic geometry by Kendall and Stoyan. And in the form we're using it is in this paper by Cassidis et al. And what it says is that for a fixed point, the probability that it takes time more than t to detect it is just e to the minus lambda times the volume of the Wiener sausage at time t, the expected volume. So you see, it's first a little surprising. The expectation is in the exponent. So in some places, this is something that's taught in the first year of grad school, but no, not where I went to grad school. So just for information, who's seen this type of formula before? Please raise your hand. Okay. So non-zero fraction, but not a majority. So let me explain the simplest way to see this. So maybe I'll go to the board here. So how do we see this formula? The point is, let's think of a thinning of the original Poisson process. So at time 0, we have this Poisson process, and let's consider a thinning of it where we consider a sub-process, only the points where in the Brownian motion by time t, they hit the disk. So this is a thinning. So consider points of the original process, or I'll call them nodes, that hit the ball of 0r by time t. So this is a non-homogeneous thinning of the original process. So for every point of the original process, we independently keep it if it hit this. Of course, for points that started very far away, the chance they'll make this distance by time t is very small, but every point has some chance. So this is a thinning where points further and further out have smaller and smaller chance to belong to this process. And what we want is the probability that the number of points the number of nodes in this thinning is 0. Now, the point is, the thinning is itself an inhomogeneous Poisson process. And so, but for any Poisson process, homogeneous or not, the probability that it's 0 is just e to the minus the overall, the integral of the intensity. Okay, so we just have to find what is the overall intensity of this thinned process. So the overall intensity is obtained by integrating. So we start according to Poisson, and the Poisson is Lebesgue measure. So it's so the overall intensity will be lambda, which is the original intensity, times integral over all of R2 of the probability starting from x that will hit B0R. So when moving according to Brownian motion by time 0t, by time t. So by hit, I mean with Brownian motion. And the x here indicates we started at x, and we're integrating dx over rd. So that's the overall intensity. But now for any point x, this probability, by just the reversibility of Brownian motion, this is exactly the probability starting from 0 that Brownian motion visits b of xr by time t. Okay. For any fixed x, we have this identification because just running the same Brownian motion backward. And now if we integrate this, then we get exactly the expected area of a Wiener sausage. So this is the intensity of the process, and we have a process of some intensity, and we want it to have 0 points. The probability of that is e to the minus that overall intensity, and that gives the formula. Okay, so one thing to observe is that this formula didn't really depend on the fact that we were working with disks. So if instead you want to know what's the chance of all these particles avoiding a square, the answer is in the same form, e to the minus lambda volume of the Wiener sausage, but a Wiener sausage obtained by carrying a square around the Brownian motion. So the Wiener sausage in general can be defined in general given any, say, compact set. It's just obtained by taking the union over all points of the Brownian path of the set plus the point. So you take this union. So that's the Wiener sausage. And so so in our case, it's a disk moving with the Brownian motion, and we take the union of all these disks. And the Wiener sausage has been studied a lot, and the expected volume is quite well understood, even the asymptotics, more fine asymptotics. So the expected volume grows like 2 pi t over log t in dimension 2, and like a known constant times t with an r to the d minus 2 in dimension bigger than 3. Note one nice thing is that in dimension 2, the asymptotics of the volume don't depend on the radius. Obviously, for short time, the Wiener sausage just looks like a disk, so the area depends a lot on the radius. But when you run it for a long time, whether you have a large disk or a small disk, you get the same asymptotics. And you can intuitively understand it by saying, even if you were carrying around a large disk, most of the area it covers will be, due to the Brownian fluctuations, it will be also reached by the small disk. So you don't gain in 2 dimensions by carrying a large disk. In higher dimensions, that's no longer true. if you go a little way from the Brownian path, you'll reach points that aren't on the Brownian path. And in higher dimensions, you do have dependence on the radius with r to the d minus 2. So this is well known, and that gives you immediately the exact asymptotics for the tail of the detection. Any questions? Okay. There is a small dependence, but not in the first order not in the first order asymptotics. Yeah, so you can, you can quantify that to all orders, but I'm just going to focus on the first order asymptotics. So, okay, so because of the stochastic geometry formula, we get the answer with a stationary target. So here's the first theorem, which is not a hard one, but it's related to an open question in higher dimensions. So in dimension 2, what happens if the target starts moving? So you could ask tough questions if the target starts moving and it knows where the other nodes are, so it tries to avoid them. But suppose its movement is independent of the other nodes. Okay, then it's very intuitive that it can't do better than staying in place. Okay? And we don't know that exactly. So the exact statement is that for any movement of the target, it's more likely to be discovered, to be detected, than if it's in a fixed place. We don't know that. We do know that in 2 dimensions asymptotically. So here you have a statement, and you see that for any movement, the probability of the detection being bigger, time to detection being bigger than t, decays, is bounded above by this same expression we had for a stationary target. Okay, the probability could be much smaller. For instance, if the target is moving at a linear speed, it will have a very high probability to be detected. The chance it will avoid detection for time t decays exponentially. So this inequality is definitely not always stated, but it always holds asymptotically. The natural conjecture is, in fact, that the probability here is just bounded above by the probability for a stationary target without any correction terms, and we don't know that. In higher dimensions, I emphasize dimension 2 because in higher dimensions the situation is more severe. There we can't even show the asymptotic results, so we know in higher dimensions, because of this Wiener sausage result, we know for a stationary target what's the probability that it's avoided up to time t. So it's e to the minus t with a constant in front, and this is the constant, a known c that depends on d times r to the d minus 2. So that's for a stationary target that doesn't move. If the target starts moving, we have a similar upper bound, e to the minus constant t, but we don't know that it's true with the same constant. So there we lose in the constant. And that's connected to an even simpler open problem that I'll maybe emphasize at the end about the volume of a Wiener sausage with drift. Okay. Now, if the target moves as an independent Brownian motion, then this inequality is an equality, at least in 2 dimensions, in terms of the asymptotic. So the target moving as independent Brownian motion is no different in terms of these asymptotics from it being staying in place. So that's the detection problem. It's the easiest one. Let me move on to the coverage problem. So this was proposed in a paper by Konstantinopoulos. How long till a large square and perhaps other large shapes are covered by this model? So you could have several notions of coverage here. Here I mean that all points are detected. In other words, the Wiener sausages spanned by all the disks should cover the square. How long till that happens? So if a disk is of side r, how long would you guess it takes to cover it? Is it r? Is it e to the r? Is it log r? No guesses? E to the r. Okay. Anyone? So everyone quite agrees with e to the r? No. Okay. Okay. What? N. There is no n. R squared log r. Okay. Let's just decide this democratically. Okay. So whoever doesn't raise their hand, they believe in e to the r, which was the first guess. Any other proposals besides r squared and e to the r? Okay. E to the r squared. Okay, let's just, who votes for something logarithmic or a polylogarithm in R? Okay, we have some people. Who votes for something roughly polynomial in R? Okay. Who votes for bigger than e to the r, so like e to the r squared or something like that? Okay. So let's see how democracy does here. So this is times 0. We wait, and it got covered pretty fast. So the answer is, in 2 dimensions, it's log r times log log r. And in higher dimensions, it's actually logarithmic. So I'm going to I'm focusing here on 2 dimensions. So in 2 dimensions, there is this log log r. And it's very concentrated. The cover time is that multiplied by this constant. And I'm not canceling the 2's here for a reason. And say the cover time divided by the expectation goes to 1 in probability. So you can really say when this is going to be covered exactly at this time. And see, this is very, actually, if you think carefully about the detection result, you can easily guess this as far as the upper bound goes. So let me just state a more general upper bound. If you have another shape, for instance, you could ask, take a line segment, a long line segment of length r, and ask how long till that line segment gets covered. And the answer is exactly half the time of a square. Okay? So, and in general, if you have any set, you can compute its box dimension or Minkowski dimension, which just measures how many little disks you need to cover it of radius epsilon, what power of epsilon that, or power of 1 over epsilon that behaves like. That's the Minkowski dimension. So Minkowski dimension of a set A is the limit, when that exists, of the number of epsilon balls needed to cover you take a log of that, divide by log of 1 over epsilon, and take a limit as epsilon tends to 0. So if this limit exists, it's the Minkowski dimension of the set. So for instance, for most classical fractals, this exists with the other notions of agrees with other notions of dimension. Like for the Cantor set, it's log 2 over log 3. And the general answer is that instead of 2 here, you just put the Minkowski dimension, and that gives the asymptotics of the cover time. So I'm not going to focus on the proof here because I want to spend more time on the percolation, which is also very interesting. But let me say something about the proof for the coverage time. So the upper bound you can just do by counting. So take the square, divide into little subsquares, and observe that if the subsquares have some side epsilon, and if you come within distance r minus epsilon of these squares, then the ball of radius r will cover them. So you can reduce it to detection problem of a lot of squares. Now, for each one, we know the probability that it will take more time to cover it is e to the minus t over log t. So basically, the equation you have to solve is e to the minus constant t over log t should be about r squared if we're talking about a square, and should be r to the alpha if we're talking about a set of dimension alpha. What? Right, thank you. So this times r squared should be about 1. Exactly, so e to the plus. So this is the probability for each one to stay undetected for time t. This is roughly the number we have to worry about. So if I divide it to squares of length epsilon, I have to, say, take here r squared divided by epsilon squared. But this washes out. This washes out in the asymptotics. So, so this part is not important because I can fix epsilon here, and just let r and t to go together to infinity. And then if we solve this, we get the result. So that's for the upper bound. For the lower bound, you have to show that this upper bound is sharp. So you want to show that before this time you're not covered. So you want to, again, count the number of uncovered squares. Take a time which is before this suggested cover time. You want to show that then there are still uncovered squares. So count the number of uncovered squares. And before that time, we know that the expectation is large. So the technical challenge is to bound the second moment for the number of uncovered squares. And here, what comes to our rescue is, again, this stochastic geometry formula. Because if I have two little squares and I want to know what's the chance they're still uncovered by some time, I can reduce it to a question of the volume of it's e to the minus, the expected volume of a funny kind of sausage we get by carrying the two squares together. So we take two squares. They're pretty far apart, typically. And so we have the Brownian motion, but the Brownian motion carries with it these two squares, and they move along at a fixed distance from the Brownian particle, and you have to find the volume of the union of these two squares. And the second moment agreeing with the first moment squared corresponds to these two Wiener sausages being typically, to this Wiener sausage obtained with the two squares being very close to a sum in a area to the sum of these two Wiener sausages with the square. So you have to control the overlap for these two, and once you do that, you can control the second moment. You have to exercise some care here because all these volumes are occurring in the exponent, so things you're used to throwing away, you have to be a little careful with, but it's still, since we understand volumes of Wiener sausages well enough, this is doable. So that's the coverage result, and again, in the general case, you have to deal with the structure of packing and covering, but I won't go into that. I want to move on to the percolation problem. So it's a classical fact that there exists a critical value so that for all lambda bigger than lambda c, you almost surely have an infinite component at any fixed time. Now, just like in ordinary percolation, I think many of you have heard the lectures by Jeff Stife and others on dynamical percolation, where you can have the percolation measure as a stationary measure, but you have a continuous time dynamics, and you ask if what you see at a fixed time also holds for all times. And the general answer is, if you're away from criticality, it should be yes, and that's also true here. And this was, in this context, so in the discrete case, it was in work, it was done earlier. In the continuous case, it's in a paper of Vandenberg, Meester, and White, that if lambda is bigger than lambda c, then you have, with probability 1, for all times, and you have an infinite component. But the question we'll be asking is a quantitative one, large deviation, to estimate what's the chance that the particle will take a long time to join the infinite component. Again, a question originally motivated by the mobile wireless people who wanted to know, if they have a very dense network, what's the chance that one customer will take a very long time to connect? But by the time the question got processed with the computer scientists and reached the mathematicians, the original people who asked it don't recognize it anymore. But we're not really troubled by that. And so this is the question. The first time the target belongs to the infinite component, what's the probability that this is bigger than t? And this probability, again, decays fast, and we want to estimate how fast it decays. And one problem in all these kind of questions is it's hard to get the answer by simulation because you're talking about small probabilities and long times. And just a short story about that. A man tries to call God. In Jerusalem, it's a local call. And he says, God, I know that for you, 1,000,000 years are like a second, and $1 million are like a penny. Could you please give me a penny? So God answers, sure, just a second. So that's kind of the problem we have with the simulations here. And so in this picture, we're starting. So again, we focus on this green node. This gray node, and the green one is the giant or the infinite component, and we want to know how long till it will meet it, and it moves around. Those could move around, or it could be. You could also think of the case where the target node is fixed and only the others are moving, and want to study what's the chance that it will take a long time for it to connect to this cluster, because that's one annoyed customer of this wireless network. So it's easy to get a lower bound, which is exponential. So first, if I think in discrete time, it's trivial, because the probability the target is not an infinite component at a fixed time s is just the probability that it's some positive constant, because even if we're supercritical, the origin might be outside the infinite component. And so that's some probability e to the minus c. And then if you want it to happen for t discrete times, it's e to the minus ct. And then if instead of unit time intervals, you think of really short time intervals, you can extend this argument perhaps with a different constant to get exponential lower bound also in continuous time, because the points don't move too much in a short interval. But is that bound the right order? So note that it's not the right order in 2 dimensions, because the t-perc, this t-perc is bigger than the percolation time is bigger than the detection time. In other words, you can't reach the infinite cluster before you reach somebody else. So that gives a lower bound in the plane of e to the minus constant t over log t. And one question is that the main problem? Is the problem to connect to the infinite component just to find somebody to talk to? And once you do, then the rest gets easier. And that's a natural conjecture or question. We don't know the answer at this precision. So that's a lower bound in 2 dimensions. Now, again, all of these things have extensions to higher dimensions, but I'm focusing on 2 dimensions. And an earlier paper from this spring, which you can find in the archive just by 2 of the authors, Alistair Sinclair and Alexander Stauffer, is an upper bound of e to the minus constant root t. So they proved this upper bound, and the main motivation for this project was to decide between that upper bound e to the minus root t, and the e to the minus t over log t bound that lower bound that you've seen before. And the main theorem of this work in the percolation part is an upper bound, which shows that t over log t is closer to the truth. Unfortunately, we can't get t over log t. We get a log to the 6. So that's the upper bound. And I think one interesting thing here is the technique, which I will indicate. So So I wanted to talk about this here for two reasons. One is one of the authors, Alexander Stauffer. I mentioned he's from Berkeley, but in fact he's originally from Brazil. And another reason is that the technique we use is one that I've largely seen here, which is multi-scale analysis, which Vlada Sidorovicius, Maria Varese, and others have worked on a lot here in related contexts, not exactly for this problem. And that's the technique of multi-scale analysis that is useful for this upper bound. So, and I feel for those who haven't seen the technique, it's a nice case to see where it naturally comes up. So that's what I want to emphasize in the remaining time. Okay, but any questions so far? All right. So of course it depends on R. You can take R equals 1. I don't remember the exact number, so but I'm sure it's not hard to look up. So maybe let me, before continuing with the proof, at least show you some simulation of this. Some, you've seen some of it before the talk. So this is the process moving. Of course, this high density, most of the time, the particle will be in the infinite cluster. Here, this is the infinite cluster is shown in green, and here I'm emphasizing the cluster of the gray point. So that's shown in green, and the other clusters are in red. So of course, what we see in this picture is, most of the time it's in here because it's in the cluster because it shows a high density. All right. So I want to indicate some of the proof. And before going that, I first want to tell you why e to the minus root t is a natural bound. In fact, when I first heard this question from Alexander Stauffer, it took me some time to first realize that it's an interesting question. It's that it's non-trivial, and after a while, I also independently of Stauffer and Sinclair realized the bound of e to the minus root t, which which is due to them. So it's really the natural bound that you first arrive at if you spend some time thinking about this problem. And why is that? So let me explain this. So right, let's take a large square. It won't be that large now. It'll be a square of side root t. The advantage of this square is that if we have a component that spans this square of side root t, then it's also very likely to already be the infinite component. Namely, the chance it's not the infinite component is exponential in its side length, so e to the minus root t. So if we're attempting to give an upper bound for the probability of order e to the minus root t, it's enough to show that it's enough to give this upper bound for the time until we reach the boundary of this square. Because if we can bound that, then once we have reached this far, the chance of not reaching to infinity is already bounded by e to the minus root t. So you can focus on this square, and the way you do that is you subdivide it into squares of area root t. So squares of side t to the quarter. Okay. And what happens with these squares? First of all, each of these squares, because it has area root t, we can be sure that it has the right density of particles. That is about lambda times its area, or at least lambda minus epsilon times its area, just because of standard large deviations for a Poisson variable. Right? A Poisson variable of total intensity root t, or lambda root t, the chance it will deviate substantially from lambda root t is exponentially small in that intensity. So once we divide it into squares of this size, then we can be sure that each square will have the right number of particles according to its area, lambda times its area, and so, and that's true not just at time 0, but at any time, because again, the probability that we're just going to consider integer times now, and for this problem, bounding at integer times will give a bound for all times. So we just have t of these times, so a factor t doesn't change. Since, if we're trying to prove e to the minus constant root t, we don't care about the constant. We can easily take another factor t in. So we can be sure that at all times, at all integer times, all the squares have the right density of particles. Okay, then what do we do? Well, at time 0, because the model is supercritical, at time 0 we have a positive probability of percolating. So the probability that we fail at time 0 is some constant less than 1. Now the problem is that the events of failing to percolate, so failing to reach the boundary here, these events are positively correlated. So if I failed once, failed twice, then the probability I'll fail again is, the conditional probability is larger. So I can't just multiply these constants, or I'd easily get e to the minus t, which we know is false. So the trick is, I know at time 0 I'm fine. Now let's, so I have some constant probability of percolating. If I succeeded, great. If I failed, then let's wait for the points to reorganize themselves. Again, according to basically a Poisson process. How long does that take? Well, we know we have the right density of points in each square, and also in a neighborhood of this large square. So there's some boundary effects that can be dealt with and I'll ignore. So look at the square here. If we failed at time 0, that's some negative information. But now let's just wait enough for the points inside this square to mix. That is, to couple with an independent Poisson process. How long does that take? Well, the answer is the square of the side length, because that's how long a particle takes to, in Brownian motion, to mix in a square of side L. It's L squared. And formally, in each square we know we have the right number of particles. We also sprinkle a new independent Poisson process with the same number of particles, or slightly less particles, but still supercritical. And then, so let me enlarge one of these squares. We have the points we're worried about where we have some negative information. These points, haven't percolated at time 0, so they're in some bad configuration, but there are enough of them. And I put down here Poisson points, the same number, or in expectation the same number, slightly less. And then I can match these up in pairs. And so once I match these up in pairs, I can wait for each of these doing independent Brownian motions to couple. So formally, for each of these, so let me blow this up again here. This is one point. This is the Poisson point. Take the usual coupling by reflecting them across this line. So they do, as this is doing a Brownian motion, this is doing the mirror image of that. And so when this one will hit the line, this one will hit it in the same point. So the time until that happens is of order the distance squared. And if I take a large constant times the side length squared, this is very likely to happen. So I'll be able to couple my points, which were in some bad configuration, to a Poisson process of slightly smaller intensity. And with some care in this coupling, I can get this Poisson process to, by reducing the intensity a little more, I can get this, the Poisson process still after the coupling to contain an independent, really a fresh Poisson process. And then I know that that percolates with positive probability. But in order to do that, I had to wait a time interval of length root t. So remember, the total time I have is t. And I have a chance to percolate at time 0. After that, I have some negative information, but by time root t or constant root t, that negative information is washed out enough. So again, I have a positive chance to percolate here. So for that to fail, there's some constant less than 1, and we can just keep going. So each constant root t, I have a positive chance to percolate, independent of previous failures, and the chance of all of these to fail will decay like e to the minus constant root t. How do you move beyond this? Because the lower bound was e to the minus t over log t. So if we want to get a better bound, then there are several changes we need to make. One is we can't start with a square of, so one change is easy. We can't start with the square of side root t. We have to start with a larger square of side t. So that's a relative, say, or t over log t. That change is painless, so we can start with the square of side t. And we want to reach the boundary of the square. If we do that, then the chance that we haven't found an infinite component is exponentially small in t. So we just have to worry about going from the origin, or from the gray particle, to the boundary of a square of side t. Okay? But then the question is, how fine are we going to divide this square? So there's we're caught between a rock and a hard place. If we divide it in big pieces, then we're sure they have the right density, but it takes a long time to mix the random walks inside those big pieces. If we put small pieces in, then we get fast mixing inside them, so we get back to a random configuration quickly, but we can't guarantee high density in these little pieces with sufficiently large probability. So the point is to stop requiring the high density at all times, just ask for the high density to occur at many times, say at most times. And that flexibility allows one to obtain the right estimate. So divide into squares which are logarithmic or some power of log. And the idea is to show that with high probability, so except for an event of chance less than e to the minus t over some power of log, well, to the beta here, but eventually it will be 6. So with high probability, at most times, and again, just look at integer times, at most integer times in 0t, all of these squares of logarithmic side length are dense, meaning bigger than lambda minus epsilon points per unit area. Okay? Since lambda is supercritical, then if we get this, then if we get at most times we have these dense points, then the same argument from before will work, because we'll just need to wait a little bit, like the log squared, and then the points will arrange themselves in a nice configuration that can percolate. So we'll get e to the minus t over a power of log. So the problem is, how do we get this density to occur at most times? Now, the point is, we can't insist on this density happening even at a single time if we insist on the time. So the important thing is to be flexible. Don't say what time you want this to be dense. Just say, I want it to happen at most times. But if you ask for a specific time, right, this little square here, the chance that at time 0 it's completely empty is just e to the minus its area, which is e to the minus a polylog. So that's a much bigger chance than we want to take. So, but insisting that we're good at most times will work. So why does that work? So again, if these events were independent for different times, we'd be in business, because if at each time we have a high probability of the square being dense, and we have lots of times, t over power of log times. So if the events of being dense were independent, then we know we have independent Bernoulli trials, even if each one has a fixed probability to succeed, which is not close to 1. We know that if it's bigger than half, then with very high probability, most of the trials will succeed. The problem is that these events are not independent. If I know the density failed at a single time, then that's some indication that it might fail the next time, and especially if I have several failures in a row, it might mean that there are no points, the points are not nearby, and so the chance I'll succeed in the next time is smaller. So the idea is, here is where the multi-scale argument enters, because remember, it's easy to control things if we take this square and divide it like this, right? The chance, so on these huge squares, I know that the chance that at any time I have a violation is, is tiny. These are, remember, this is a t by t, so these are squares of area order t squared. So for these, I know that they're going to be good for all time, and I can keep dividing for a while, until I get the squares of about t, of area about t, that is squares of side root t, and there I start, I can't insist on things being good at all times. But what we're going to do is just, in the multi-scale approach, is just insist that we have a high density of, that most times are good at any given scale using the previous scale. So the large scales are fine, and we just have to do the induction step going from one scale to the next. Now when we do the inductive step, we're going to lose some of the good times. So some of these times when we have high density, we can't retain all of them, but the idea is to just lose a tiny fraction, enough that we can afford these losses through log t scales. So what happens in an inductive step? We assume that we're okay in some scale. Okay, so I can't draw very many scales. So assume that this is already some interesting scale where the area is less than t. Okay, and now I want to, and I assume that I'm okay here. So at most times, again, all of this has to be quantified carefully, but I don't have time for that. And you can, the paper has already been uploaded on the archive, so you can look at it if you want. So at most times, we assume that at this scale we're okay. At most times, these squares have a high density. All of these squares of this size. And now I want to go to the next size. Okay, so now let's look, besides the spatial picture, let's look at the time axis. So we know that most times are good. We have an occasional failure for the large scale. Now we look at the finer scale, just finer by say, a constant factor. So what can be the trouble here? We know that at this scale we're good, and not just in this square, but in all the squares, we're good at the larger scale. But we might have trouble here. What does that mean? That we have maybe more points here, more point in the other squares, and maybe not enough over here. So here the density has dipped dangerously down. That might happen. At any time, if I look at the fixed time, I have a good chance of the density in all of these being about the same. But I can't insist on this happening at all times. So I will have some bad times where this will fail, and this means that from these times I will lose some small fraction. The problem is, how do I recover from a failure? How can I get independence or approximate independence of the different failures? And that's where the previous scale comes in. Because suppose I know I have a bad time. So this square had just a few points. That's worrying. But we can easily recover from that because we know we have enough points around, not just here, but also in the adjoining squares. So if we wait now a time which is of order of the square of this length, then everything will, the points can have enough time to rearrange, and you have a nice balancing. As you go down, you can check that always the probability of failure can be controlled, though it's different reasons at different scales. So when the squares are relatively large, it's unlikely to deviate from the right density, but it takes time to refresh. As the scale gets smaller, it becomes easier for the small, to have deviations from the right density, but you recover more quickly. And if you do the calculation, these factors exactly balance, and you can get this e to the minus t over a power of log for every step of the construction until the end. So that's, as I think as much detail as I can give. So the point, what is the point of the multiscale, moving back from the details, that each time the larger scale gives you the required independence at the next scale to recover from errors, from bad events. That if you just wait a short time, there are enough points around, they can move to refill. Well, if you didn't have the previous scale, you might worry that if I'm looking at a box and it's low density for several times, well, maybe it indicates that the points have all moved far away, and then I'm unlikely to recover in the next step. Okay. Thank you for your attention. Yes.
Do you have a guess for the right power for the writer? Just doing this?
Well, my guess is still that it's e to the minus t over log, so that that it's still just the single thing. But it's certainly not log to the 6. It's not log to the 6. But whether it's log or log squared, I really can't tell. It's still, we saw that with substantial more effort, we can probably make the log to the 6th to log to the 4th. We didn't want to invest that because that's not where the truth lies. If anyone can see a way to get the upper and lower bounds to match, that's in my mind worth an effort here. But as long as the upper and lower bounds are different powers of log, I'm not that thrilled by the exact values. Of course, it is one thing why it is interesting if you can improve is just in terms of technique, because these techniques are really applicable to a variety of problems. We don't have that many problems that I know of where random walk Brownian motion estimates interact with percolation estimates, and these are cases, natural candidates for multiscale. One series of works by Harry Kestin and Vladas has this kind of combination. This is another place where we have this combination. So I think it's interesting at the level of technique. If you can improve it, it means you have some new idea which may be interesting. Ron, you had a question?
Yeah. Is it expected that F criticality for the
Yeah, well, I guess it's natural to expect. I don't think many people have tried to prove that. Okay.
You had the probability of non-detection times this e to the minus 2 over log t.
Yes.
How does that event look like? Does it have a typical structure? The point is surrounded by a big hole or something like that?
Yes. So, yes, the point is surrounded by a big hole, and you can try and measure that hole, but there is some kind of quasi-stationary distribution that depends on how long you want this to be. Roughly, right, there's a hole, yeah. So there's a hole. Its area is t over log t. So the coverage result is not the large deviation estimate, right? It's just uses large deviation as a tool to find the typical time to cover. So I guess, so your question is about the percolation? Right, so at the percolation, this is at really the heart of the matter. Is the main reason for non-percolation just isolation or non-detection? So non-detection is fairly easy to understand, but is the non-percolation mainly due to just the point has stayed lonely up to time t? That's really, I think, a key question which we don't know. Actually, one thing I promised before, which I should deliver, is what is the simple open question that is suggested by this? This is a question about the Wiener sausage. Let me just spend half a minute to state it, which is, so consider the Wiener sausage obtained by Brownian motion with a drift. So you take Brownian motion plus f of t plus a ball of 0, 1, and you take this, right, and you take the union t from 0 to capital T. Look at the expected volume. So is this expected volume minimal for f equals 0? So at least asymptotically, it is minimal in dimension 2, which is behind the detection result I mentioned to you. But even in dimension 2, I don't know that it's exactly minimal. And in dimension 3, we know that the expected volume of the Wiener sausage grows linearly. And the constant is known for the ordinary Wiener sausage. If you add a function, we can still show any function. We can still show it grows linearly, and there's a uniform lower bound for all constants, for all functions. But that uniform lower bound is less than what you have for f equals 0. So in dimension 3, I don't even know this in the asymptotic sense. I lose a constant. But if you think about it, it seems like the moment you add this drift, you should decrease the expected volume. Now there are many methods to find the expected volume of the Wiener sausage relying on potential theory. Only some of them extend to work with the case with drift. In fact, I only know one that works with drift, and that one is not precise enough to answer this question. But maybe if someone finds out, I'll be glad to talk to them. We have actually a variety of applications of this, if it's true. So anyone who finds, let me know. I'll invite you to visit, and we can talk about it. All right. Any other?